Well, thank you, John, for the invitation and introduction. John is my neighborhood, so sometimes I walk around my house, taking a walk after dinner. I saw John right there, doing the trash, pulling out trash. It's actually fun to see that. So I just got back from China, still on the jet lag. So if there's anything I say, outright they're crazy, don't be surprised. Blame the jet lag, okay? So this is my third energy seminar. The first one I was talking about battery technology. Previously, I talked about a Bay Area PV consortium on the solar. This time, last couple of years, you have seen California's water problem. We have been doing water over the past 6-8 years or so. So I feel like it's a great opportunity to share with you the water problem. To a very large degree is an energy problem. Of course, it's a cost problem. I borrow a slide from my student Chong's thesis defense. So every day we use water. Right? We use water, we drink. So we do the kitchen work, we take shower, we wash clothes. We certainly also flush the toilet. So guess how much water do we use every day? Any people have a good guess?
50 to 70 liters a day.
70 liters a day. That's great. You save a lot of waters every day. What's the best guess right here?
20 cubic feet a day.
20 cubic feet. My God, I need to I need to convert. How many liters?
4 pounds per cubic foot, 8 pounds per gallon.
Well, let me give you a number, right? So, well, let me ask you to guess first. So, which one consumes most water? Everyday use. If you are from my group, you are not allowed to say it. Any guess right there? So turn out to be, you see right here, this one. It's a lot. Yeah, flush the toilet. So this is big also. This is, well, we only drink 4 liters of water right there. So this is consumed per capita per day, the consumption. And Tong's analogy, this is what, 25 pack of water right there in the supermarket. So that's a lot of water. Also give you a perspective, if you run 5 minutes of faucet, the energy it takes to make this water, it's like 60 watt of light bulb for 22 hours. So save water is very important. And also, giving this big number, 300 liters per capita per day, we need to be aware of, so in the world, there's other people, a very big population in the world using water that's less than 3 liters per capita per day. So imagine if you want to save water to this degree, your life will be completely different. So water is, certainly this problem exists, it's a huge, huge problem. What do we want? We want water that's clean, that's fresh. Clean in the sense, no pollution, no organics, no heavy metals, no viruses, no bacteria. We want it to be fresh. We don't want a lot of salt in there. There's now needs to think about even more about water desalination, thinking about how do you take out the organic pollutants and also heavy metals in there, and the biopathogen as well. So these are the demands right there in the world. And now let's look at the water-energy connection, under this background of energy seminar. So this is the data I took from here, the sources here. And for different water sources, to treat 1 million gallons of water, how much electricity it takes. Going from bottom, actually recycling is the best way. Consume very little energy, recycling. All the way to the most energy intensive one is to do desalination of seawater. You have 600 millimolar of salt concentration in there. Let me use a different unit right there. I don't get a sense of a million gallon, how big that is, but I have more sense of cubic meters. So 0.3 kilowatt hour per cubic meters from recycling water all the way to about 10 times more. That's 3 kilowatt hour per cubic meters for water desalination of seawater. So this energy consumption can be big. Now let's look at how big is that for the whole world. Whole population, the whole world is about 7 billion people. Let's assume we have the lifestyle of the United States. Everybody has the same lifestyle, 300 liters per capita per day. So we will consume 2 billion cubic meters per day, roughly. And the energy consumption somewhere is 0.6 to 6 billion kilowatt hour per day, depending on you are doing recycling water. If you do all waters by desalination of seawater, you are going to have this 6 billion kilowatt hour per day energy consumption. To put into the power, assume you have solar cell running 24 hours a day. This is certainly not a correct assumption right there. So this is the power you are talking about, 25 to 250 gigawatt, continuous going, this power. So in California, our electricity power consumption, if you download the California ISO, you see that right away. We have about 20 gigawatt, and the peak time is about 30 gigawatt. So average, let's say about 25, close enough. So you basically take the whole California's electricity we consume, the whole California. Doing the recycling, the less energy consumption of a water source, you can then supply the whole world of one day, right? Use every day. This is power, so you basically need to consume the whole California electricity. So this is the amount of energy we are talking about. We need to consume to treat water. It's very likely we need to go to the more and more of doing the seawater desalination. Then this number will go bigger. So this is 10 times of California electricity. So the water and energy, certainly the linkage in the past already happened. Hydroelectricity. This is Three Gorges Dam right there, and then recently re-emerged as a very exciting topic is use electricity using sunlight to split water to generate hydrogen. So their linkage is right there as well. But this will not be the topic today. So today I will just talk about the things related to how do we treat water. How do we think about desalination? How do we think about remove organics to generate electricity? And how do we do a water disinfection? So past 20 years, actually nanotechnology bring very exciting opportunity, new ideas, new materials, new devices, new mechanisms for treating waters. So here are some of the pictures showing in the past 20 years also. You have seen this carbon nanotubes, graphenes, quantum dots, nanowires, and so on. And these materials development have shown a very good size, shape control. How do you control composition? How do you generate heterostructure in a new way? And how do you put this nanostructure together to do the assembly, to perform the function which didn't exist before? So these become some of the key research guiding my research group using nanotechnology to do water as well as air for the environmental, the whole package. So today I will just show the examples how we think about doing water. Let me share with you about water desalination. We invented a couple of new device concepts. One is called water desalination batteries. You probably haven't heard that much about before because it's only our group is doing it, and also seawater batteries. This work was initiated by my two postdocs, Fabio and Mauro, and Meng joining the team, and this is in collaboration with Craig Cradle right here in environmental engineering. Well, let's look at water desalination. The dominating technology for water desalination is indeed this process called reverse osmosis. So in this device, there's a membrane in the center. This membrane is permeable to water molecule, but not sodium ions, not chlorine ions. So what you do is you use high pressure to push on water. We know this osmosis process is that if you push the water and then the molecule will like to go to the other side of this membrane, and only water molecule can go through, then the fresh water will come to this side. So that's the idea of how you get the fresh water out, remove it from the seawater with a lot of salt in there. But when you think about this, this technology has been around for multiple decades. It's indeed from outset, it's not a great idea. So you see seawater mostly is water. Then you have 600 millimolar of salt. Now you try to take all the water molecule out, separate it from the salt. That's very energy intensive. You're moving a lot of molecule from small amount of ions, right? Thermodynamically, we need the energy. We know the energy needs is indeed only 0.7 kilowatt hour per cubic meter. In reality, this is the number consumed. 3 to 5.5 kilowatt hour per cubic meter. So that's 5 to 8 times of what thermodynamics tells you. That's because this membrane, when water molecule go through, you build up a lot of kinetics, dissipation of the energy right there, right? The molecule get dragged, can push through those membrane. It takes a lot of energy. Can we do much better than this idea? That's the key questions my group tried to answer. So we come up with a different idea. We know in the past 20, 30 years, there was a lot of progress in the energy storage research on the lithium-ion battery technology. There's so many new materials coming up, to store lithium, get lithium in and out. There's also so many materials developed to get sodium in and out. And then if you think about this, you have a solid materials. You can take an ion, sodium or lithium, put them into a crystal structure. If you find another materials, you can take chlorine from seawater and put into the crystal structure. You remove these ions from seawater. So we identify two materials right here. One is a low-cost manganese dioxide. The manganese dioxide can take sodium in. This is a sodium chloride from seawater. And the silver can take chlorine out, forming silver chloride. So silver and silver chloride reaction is very well known, and electrochemistry is a very common use. So-called reference electrode is silver and silver chloride interconversion back and forth, very reversible. And manganese dioxide is also known can take sodium in and out reversibly with very little energy loss right there. So we construct a new device. We call this as water desalination batteries. So we take MMO, that's a sodium manganese oxide, and a silver. And then you're doing the battery discharge. This is the seawater right there as an electrolyte. You discharge the batteries. Sodium will go into a manganese oxide. Chlorine will combine with silver, generate silver chloride. So by the schematic drawing, you see the lower concentration now. Each of those balls right there indicates ions. You're now taking away the salt from the seawater. So you get the fresh water. You flush this fresh water out. You flush in. The seawater goes in. Now, once the seawater goes in, you do the next step. That's you charge up these batteries. When you charge up the battery, you dump these ions, silver, sodium, and chlorine, back into the seawater. So this concentration becomes higher. So fresh water coming out from here, more concentrated, salty water flow out. Now you put it in seawater again and repeat the cycle. So every time when you come to here, you have fresh water. And you are doing a discharge of the batteries and charge of the batteries. And then you recover back. This is the whole thing. Now you can do charge, discharge many, many times. You just repeat using these batteries for the water desalination. So this is a curve you will expect. What happens, you start right here. This is in the beginning. Step 1, you discharge the batteries, put sodium into the crystal structure, chlorine into the crystal structure of the electrode, and then you flow out the fresh water, flow in the seawater. The voltage will jump up, and then you do the charging and come back. This is the voltage versus the charge curve. This is also saying the voltage versus the sodium, amount of sodium ion or chlorine ions you put in or take out. So this whole loop really produces the amount of energy you need to put in to do water desalination. Okay? This is the really close to the thermodynamic limit. The difference between the voltage right here on the top and the voltage in the bottom is defined by the thermodynamic potential depending on different concentration of the salt. The higher concentration, the voltage curve is on the top. The low concentration, the voltage curve is in the bottom, plus some of the kinetic loss during this process. So with this idea, we chemically synthesize sodium manganese oxide nanorods, showing right here. 1 micron scale bar, you see these nanorods, they have diameter a couple hundred nanometer also. The reason to use nanomaterial is because high surface area, small dimension, and the distance for sodium ions to diffuse in and coming out is short, so you can minimize the kinetic loss. And you measure the voltage curve charge and discharge. This is the curve of sodium manganese oxide. The blue is silver chloride, charge discharge curve. And to give you an idea, when you put in charges, how the voltage respond to this current charging and discharging process. This is experimental data. We measure the potential. We measure the voltage between the two electrodes. Now you start the step 1, discharge, take out the sodium and chlorine from seawater, put them into your electrode, and you take out the fresh water and put into seawater and charging it, and now come back and change it back to seawater. This is a 261 millijoule of energy we put in just by measuring these areas. And for a very small device, we measure. And using this energy, we actually take out 25%, roughly 25% of sodium chloride from the seawater. So indeed, this is the real seawater we did experiment on from Half Moon Bay. So this is actually work for the real environment. Now this is a more careful measurement. After you do the taking out the sodium and chlorine, you actually measure how much you really take out. You see sodium right here. So this is a parameters I want you to focus on. This is so-called Coulombic efficiency. I know how much current I put in and the time, electrical current. I can calculate the charges I put in, how many electrons I put in. And then I calculate, and after I do this desalination, I can measure the concentration still remaining in the water, right? Now 40% of the electricity, taking out sodium ion, about less than 1% is potassium. We actually can also take out magnesium, a little bit of magnesium as well, and a little bit of calcium. You see chlorine on the anion side, this is 87%, Cation, positive charge, is 100%. Anion, that's negative charge, has its own 100%. Here is mainly chlorine. So eventually, this is the desalination efficiency we have. 50% of electricity we put in, we can take out the relevant cations. So where does the other electricity goes? Where do they go? And in the seawater, you have organics in there. Some electricity probably have side chemical reaction that are consumed by those organics. Also, potentially, there could be some other things going on, other ions, or sometimes water gets splitted if you go to high voltage, right? They generate a little bit of hydrogen if you don't control it well. But overall, this is pretty good. 25% desalination. we get to about consume electricity, we calculate it, 0.3 kilowatt hour per cubic meters. If we do a 99, only I assume linear extrapolation, of course, and the real technology, this won't be linear. We're going to consume more energy than this linear extrapolation. If we water doing a 99% salt removal, will consume 1.2 kilowatt hour per cubic meters. We are doing pretty good. Theoretical is 0.7 kilowatt hour per cubic meters. So we are somewhere close to about double also. This is much better than a reverse osmosis process. So this idea certainly is a first demonstration. There's a lot of things we need to figure out. How do you engineer? How do you flow water in, flow water out? That also consume energy as well. And the whole picture, whether this can make it into the real technology or not, we need to study more. Now let's look at this idea, the same one. Instead of running it this way, I was telling you running it can go this way. That's water desalination. But you reverse the cycle, going this way. That becomes the seawater batteries. So what's the idea? We know at a given time, we have river, that's fresh water, flow into ocean. Ocean has 600 millimolar of salt. The river water has about 6 millimolar. So it's about 100 times difference. 100 times difference, this is your thermodynamic energy, your entropy energy. If you take the log of 100 times, for sodium ion alone, that generates about 120 milliwatt of voltage difference if you use that as electrolyte for the battery. And chlorine generates another 120. Adding together, it's 240 milliwatt of voltage difference. That's the energy you can take out. So if you reverse the cycle, now you are seeing this. You have this the same thing, sodium manganese oxide and silver chloride. You have river water. There's not much of salt in there. Now what you do is you charge up your batteries and the river water. You put the ions into the river water. Now and then you flow in the seawater. You take out this. You flow in the seawater. And then you do the discharge, step 3. So what happened is, now this becomes charging, this becomes discharge. Turn out to be discharge voltage is higher than charging. You gain energy out of it. Discharge voltage is lower, discharge voltage is higher than the charging voltage. So you actually take out the energy from the salt concentration difference between river water and the seawater. So we actually experimentally measure and demonstrate, a curve like this, measure the voltage versus the amount of charges you put it. So we don't have to go to details of this curve right here. And this is a number of cycles we can do. You can do charge, discharge, charge, and discharge. This is 100 cycles, no decay, with energy efficiency of 74%. So what does this mean right here? Every year we have a lot of water going to river, going to ocean, from river into ocean. So you look at the distribution, South America has the most because of Amazon River. The floods is so big right there. And Africa is quite big as well. Canada has a lot of this fresh water going to ocean. Before they go into ocean, certainly I'm not considering, when I talk about this, I'm not considering any environmental impact yet. There will be environmental impact if you do this. Is the fresh water coming in? Let it flow into your seawater batteries, with ocean water and the fresh water back and forth. You actually take out the electricity. The potential of the whole world is somewhere close to 2 terawatts of power. You can generate it. So the whole world energy consumption, the power consumption is somewhere around 17 terawatts right now. So this is not small. It's actually quite big. But there will be environmental impact right there. That is a question I don't know how to answer. I'm offering an idea right here. How do you take out the energy we wasted as we are speaking? Fresh water going to ocean is 2 different salt concentration of solution mix that generate heat get wasted. So this area is still going. Indeed, working with Crack Cradle, a joint student Meng demonstrated, you don't have to just use river water. The wastewater we discharge to the environment every day. So you can use those wastewater as well. I won't go into detail of that. Now let me move on to the second areas of water treatment technology I would like to share with you is on the how do you utilize organics to generate energy. We first work on microbial fuel cells, and then later we find out where the energy loss is. We actually invented a new idea called microbial batteries I'm going to share with you. Shin was a graduate student jointly between my group and Craig, and together with Meng working on this project. He's now in a Caltech as a postdoc looking for academia job. So let's look at organics in the wastewater. So every day, right, we take shower, we use soap. Soap molecule is an organics. In the kitchen, right, we use a lot of ways. You flush down to the, you grind it up and then go into the wastewater system. So actually, there's a lot of organics right there. If in the environment, the organics content is too high, that's not good. You can grow bacteria, you can grow too much other stuff right there, and that's not good. So you need to treat it. You need to oxidize those organics. And organics is an energy source. And it turned out in the environment, the microorganism, they can consume these organics. There's a bunch of them, many different brands. And they actually can generate electrons. And these electrons, when they generated, they cannot be taken out. This electron will be used by these bacteria, these microbes, to generate organic molecule. They can use by themselves. They can grow. They propagate, they're going to form more of those microbes. But if you can use the electrode to take out those electrons, and then the bacteria, the microbe won't grow that much, you generate electricity. So this is an idea. This is a schematic drawing of this microbe right there, sitting onto an electrode. Turns out to be there are three mechanisms. You can take out these electrons. People have studied in this paper. So one is direct electron transfer. So this electrode will pick up electrons directly from microbe. The second one is through these electron mediators right there. So there's some redox molecule pick up this electron, this molecule diffuse around and dump this electron to the electrode, and then diffuse back to pick up more electrons. The third mechanism is this a microbe. Turn out to be they grow out a lot of hands. And the nanoscale, a couple hundred nanometer scale or below. This is called bio nanowires. And people reported the electrons can move inside and transport to longer distance. You can pick up the electrons at the end of these bio nanowires. So in order to have these microbial fuel cells to work well, you want to optimize, maximize the electricity collection efficiency. So basic device will look like this. You have an electrode, we call it anode. You have let these microbes grow on these electrodes, and then you construct a full electrochemical cell. And this side is oxygen from the environment coming in, oxygen gas, pick up the electrons. This electron really generated by oxidizing the organics, the waste organics by these microbes, and ship it out, coming to this side. Oxygen oxygen gas becomes OH minus. This proton generated right here during oxidation. So these two meet, then you balance the charge. It becomes charge neutral. So you form the full circle right there. So in order to make that a good electro interface with the microbes, we learned something from the past 20 years development using, for example, carbon nanotubes. That's right here. This is, it's very conducting, diameters a couple nanometers also. And you can buy it now, and forming, this is powder, adding water and surfactant and disperse them into an ink of carbon nanotubes. And then you can put in a textile, the stuff you wear, get it from Walmart, right? When we do the experiment, students went to Walmart to get it and dip it into this carbon nanotube ink. This ink will just wet this textile. You take it out, you dry it. So what you have right here, and each of these textile fiber, textile consists a lot of fiber. on the fiber surface, a lot of carbon nanotube coating onto, forming a layer onto this fiber. Now this carbon nanotube is so conducting, this network is conducting, so the whole textile becomes conducting. You can look at the cross section right here, these carbon nanotubes sitting right there. And when you look at this textile, this is 500 micron scale bar, so there's a lot of big pores in there. Bacteria, microbes in the size about a micron also. This is so much bigger than the microbe size. So the microbe can go in and stick onto the wall and then grow it, grow on this structure. So, and then we use this electrode to make this microbial fuel cell using this H shape of flask right there. In the middle, we put it into a membrane. You have one electrode on one side, that's you can grow bacteria. The other side is your oxygen electrode, to pick up the electron. And we compare the state of the art at that time. That's this carbon cloth. This is the carbon fibers, woven into this cloth right there. That was the state of the art at that time. We want to compare our carbon nanotube textile, how well it performed versus this carbon cloth. The first thing we notice, this is our carbon nanotube textile. You see each of these nanotubes sitting right here, wire-like structure, right, forming a film, nicely sitting onto the textile fiber. Now each of these rod shape of structure, this is under scanning electron microscope. These are those microbes. And they sit very happily. How do I know they're sitting very happily? I'm going to show you the data because they perform the job. So only happy people can be efficient. So that's a rationale. So you see this bio nanowire growing out, right? And then we compare, the left side is the carbon cloth, the state of the art, and the right side is our carbon nanotube textile. And this carbon cloth, this fiber right there is very densely packed. You see most of this micro forming this biofilm coating on the top surface. But with the textile right there, because it's highly porous, big pores in there, and the microbe can actually go inside and grow very deep. Each of these fiber surface now, they're covered by microbes. Now you can have a lot more microbes and close contact with this conducting textile fiber. So these provide a lot more microbes to do the job. This is really just the this biofilm, the bottom part of the biofilm. When it's closer to this conducting carbon fiber, then you can have direct electron transfer. You can have some mediator, redox mediator diffuse. There's a diffuse distance. If it's too far away, it's not efficient to collect the electricity. So in comparison, you will expect this is much, much better on the right-hand side. So let's look at the affinity, the contact. This carbon nanotube coating is actually rough. Actually, rough surface, the microbe will really like it. The flat surface is like there's nothing to grab on, so the microbe's attachment won't be strong. So if you compare these two, this is our case. That's the rough carbon nanotube surface. We expect this membrane of the microbe, can go somehow close to conformal on the surface. There's more point to grab. It's rougher. So, and this will enhance the charge collection of these two pathways right there. And also this direct membrane contact is so much better. One image showing right here is this a micro, this bio nanowire go embedded underneath the carbon nanotubes. So this attachment becomes much stronger. If you compare these two, this is the testing. Initially, you grow these microbes onto the carbon cloth. This is carbon nanotube textile. And you do a little bit of sonication, right? Sonication means what? You try to knock away, the stuff, stick onto something, and then you can use sonication power to do that. And the CNT, carbon nanotube textile right here, these microbes still stick very well after sonication, but this one just get cleaned up. So that tells you this carbon cloth, the attachment is not strong enough That's not good for the charge collection. So charge collection on the right-hand side will be expected to be much better. So this also shows us so-called impedance. We can use AC impedance using alternate current or voltage to measure the charge transfer impedance between these microbes and your electrodes. So this is the one using carbon cloth. This is a semicircle. Without teaching you how to read this curve, you have to believe me. That's how you read it. The diameter of this semicircle from 100 to 400 give you 300 ohm for the carbon cloth. But for our case, the semicircle is so much smaller, so this becomes about 30 ohm. You have 10 times less resistance. That's because of strong attachment, very strong attachment of this microbe with your electrode. So it turned out to be, we have the power output, we measure the current versus potential. The red curve is our CNT textile, carbon nanotube textile. We can have 2.6 times more current than the one of carbon cloth. That was considered the state of the art of that's carbon cloth. So we have a lot more energy collected compared to the past material, electron materials. So this is due to, we have internal, so-called internal colonization. So microbes can go inside of the electrode through these big pores, and the strong, affinity of the microbe with the electrode surface. And then if you compare, look at this, and then we were searching for, better polar structure. And the first time we did it was on a textile. But textile has a problem. You see each of these fiber, one fiber going this way, the other fiber going that way. So what about the crossing point? Actually, some of the fiber don't touch. Carbon nanotube coat on the surface. You want to form three-dimensional continuous pathway. This point doesn't cross, so that's not so good. It turned out to be you can find much better three-dimensional polar structure. That's your kitchen use. Sponge, wash dishes. Those sponge has these beautiful pores right there in the order of half a millimeter also, and these allow you to do the micro grow inside. At the same time, this sponge material, they are interconnected. There's no those junction point, they don't have those problems. So we use the sponge and then grow carbon using the ink, carbon nanotube ink, to deposit carbon nanotube on the surface. This is sponge before. We call carbon nanotube. This is after. Dip it in, take it out, dry it, and then it's very fast. And so we put the electrode right there, making this brush type of structure of our sponge. And use that as an electrode. This sponge, kitchen use sponge, right? You can pull on it. It's flexible, stretchable. Now you have a stretchable electrode right there. So now let's compare. So this is how they look. This is our initial textile, carbon nanotube electrode. After we use this for 1 year, so this experiment, if you do this experiment, a graduate student can only do this for five times, right? And 5 years they graduated. So this is after 1 year. You see, this is microbes. They already kind of grow into a film. You don't see this polar structure anymore. And this sponge have more uniform pore, right? Big pores right there. And you can still see this hollow space. This is important. That's because these microbes need to consume organics, right? The wastewater coming in with this organics. If this block all the pores, and then the microbes inside this electrode, they don't have nutrition anymore. They might die. Number one is the second one is the concentration of organics become lower, and they don't do that much job. Only the top surface can do the job. So this is a better electrode. We actually show that using this sponge. This is much better. However, let's look at what's the limit of this technology. In Stanford and Palo Alto every day, so we put in so much wastewater, right? It needs to be treated, consume that organics. So what's the energy efficiency right there? We found energy efficiency is actually not that high. Guess what? It's only 3%. If you consume that organics, you know how much electron how many electrons you can take out. You calculate it. turned out to be you can only get 3% of energy out. So why is that? Let's look at this structure right here. This is your anode. This is where our bacteria grow. The cathode right here is oxygen, pick up electron, become OH minus. So the voltage loss is known in the electrochemistry. Oxygen, this molecule is tough. You want to split water, generate oxygen gas, or oxygen gas coming in, pick up the electron, become water. This loses a lot of potential energy. It's kinetically very slow. So we have voltage loss on this electrode. And then not only that, we also have oxygen diffusion loss as well. If this oxygen coming in, bubble in the oxygen, some of the oxygen molecule dissolve into water. They're going to diffuse through this membrane and come to this side. Initially, you want this electron pick up the electrons from these microbes, but oxygen molecule just diffuse in. Oxygen can directly pick up the electrons, and then you lose the energy. You lose a lot of electrons. Yep, and then these will be also having the biofilm grow. These can grow biofilm and block these pores as well. So, and we actually invented something. I'm going to spend 1 minute to explain this. We actually replaced the oxygen electrodes with solid material, no gas anymore. Let's say we take a silver, and when you pick up an electron, you can go silver oxide, become silver. You can regenerate silver, become silver oxide, and put it back in again. You don't need to use membrane anymore because you are doing solid electrode. So you are not worrying about these species intermixing together. And we actually show silver has very little voltage loss. You are not dealing with oxygen gas. And compared to with traditional of oxygen gas electrode, this lose 0.9 watt. This only lose 0.25. So you have much better voltage gain. Eventually, we actually have fuel cell efficiency, microbial battery efficiency. That's about 10 times of microbial fuel cells you can do due to this reason. There's no oxygen molecule diffusing anymore. I think the time is up soon. Looks like this is going to be a shorter talk than I expected. I'm going to just go to the summary slide. So I was using the example of desalination and these organics to show you the new materials, new nanomaterials coming in. Well, you can do things differently from before, much efficient way, there's new ideas and consume less energy. What I didn't have time to talk about is disinfection as well. So we have a disinfection technology that can punch a hole through bacteria and viruses and kill them very fast, yet consuming very little energy. At the end, let me stop here and by thanking my collaborators, 3 research groups, Craig, Alice. I didn't talk about disinfection. With Sarah, we started the disinfection technology at the beginning, and multiple students, whether they are joined or belong to my group. Thank you for your attention. I'll be happy to answer any questions you have.
What kind of microbes are good for the purpose?
So there are actually a bunch of them. We have done a sequence on them. Yeah, the name I don't remember. Sometimes the name is too long. There's some specific bios that consume different organics. So there's a huge number of population right there. Yeah, there's some very efficient for certain organics. So it's good in the real environment. You can do a mixture of that. After mapping out what a microbe efficient to what organics, then you can choose the brand mixing to tailor towards the what wastewater you are dealing with. We have not had that yet. I would love to do that. So it's too early. First of a couple papers on this. We haven't understand the whole spectrum of challenge. And when you build bigger systems, so we'll need to wait for a few more years once we do to pilot scale prototype, and we will know more about the cost.
I don't fully understand. understand much of this topic. I'm just going to guess at something. You can correct me and get me back on track. Are you saying that we can take polluted water and purify it, use it as a battery, and make energy?
If it's polluted by organics, yes, you can consume the organics. You can make energy. If you're thinking about polluted water by heavy metals, and not for energy purpose, if it's heavy metals, we'll take out the heavy metals using certain mechanisms I didn't talk about today. Yeah, depending on what pollutants we are talking about.
So how many moles of silver do you need for a terawatt year?
So silver will not be the way to go. We actually have a new material that's much cheaper to replace silver oxide. It's actually called Prussian blue. It was made by 1 million tons per year, so that was a very low cost. So we have new materials now replacing that.
Well, E, thanks again for a fascinating talk.
Well, thank you.